Hi, everyone. Thank you for joining us for the Host Addressable Subsystem Local Memory webinar hosted by the NVM Express organization. We'll get started here in just a couple of minutes. Thank you. Hi, everyone. Thanks again for joining us for the Host Addressable Subsystem Local Memory webinar hosted by the NVM Express organization. I would like to take a moment here to introduce our speaker today, who is Jason Molgaard from Solidigm. And then I will pass off to Jason to start presenting.
Thank you, Megan. Hello, everyone. Thank you for joining. As an outline for our webinar today, I will talk about the motivation for why we want to have a host addressable subsystem local memory, also known as SLM. We'll take a look at the theory of operation, talk about the benefits that host addressable SLM brings, and then look at use cases, which happen to be computational storage related, but not necessarily usable only for computational storage. All right, so why do we want to access subsystem local memory using host addressing? Well, to begin with, we have NVMe devices providing host accessible memory in the form of SLM. So SLM has already been defined in the NVMe specification, and we have the ability to access this memory that's now in the device using SLM command set commands. If we could access this memory with a memory protocol, it would be more efficient, and we could enable things like peer-to-peer communication using a memory model. And one of the things we want to enable is CXL. And so if we used CXL to access that memory, we could enable cache coherency of that memory with the host. From a computational storage use case, computational storage drives will have more host accessible memory than a traditional storage device, although that isn't necessarily only applicable to computational storage, like I said. Computational storage drives also do benefit from peer-to-peer communication. All right, so let's talk about how does it work. Well, there's SLM namespaces will be accessible by one of three mechanisms. So we have the SLM command access only, which is what we have today. That already exists. That's in the NVMe specification and is available for anyone to use right now. And we're going to enhance that with two additional modes. So the first mode is SLM command access and PCIe base address register or bar access. So that is one additional mode. So the commands are obviously still there, but now we've also are assigning an address to the SLM using the base address registers that we're all familiar with. And the other new mode is SLM command access and CXL host managed device memory or HDM access. So here we still have the commands, but then we also can use CXL, like CXL.mem, for example, to access the memory that's in SLM. At boot time, the mechanism of access for each namespace is determined. So you have to pick one of these three, that you can't have more than one of the three options for any particular namespace. So the device is going to request bar space for all SLM namespaces that may be bar accessible. And a CXL NVMe aware driver will call CXL kernel services to discover and configure any CXL HDM SLM memory that is in your device. So to understand that a little bit better, let's take a look at this example memory diagram. So like I said, this is an example. So what we're looking at here in the very middle of the slide is a memory map, and this available device memory. So we're essentially looking at what's the memory that's available in the device. So if we kind of start at the bottom, we've got device registers. Above that, we have non-SLM CMB. CMB is a controller memory buffer, and that's obviously well defined in the NVMe and readily used in various products. Above that, we've got some namespaces. We have namespace ID 1 and 2. The intent of this device is that it wants these two namespaces to be using the PCIe bar addressing to access that SLM. Namespace IDs 3 and 4 are above that in this example where we want these two namespaces to be accessible using CXL HDM access. And then, of course, to make a complete story, we have namespace ID 5 and 6, which are going to be command access only, the same that we have today. So what's going to happen at boot time, if we look over on the left-hand side of this picture, is the device is going to request bar space for the entire region up to and including namespace ID 4. And the reason for that is for this particular device, and again, this is just an example, it would like to have namespace ID 3 and 4 be CXL HDM accessible. However, if if the host is not CXL aware or is not able to support CXL for whatever reason, it would like those two namespaces to be bar accessible instead. So we have to request all of that memory at boot time, all the way up through namespace ID 4. And then later, if we look over on the right-hand side, as the boot process continues, the host discovers, oh, namespace ID 3 and 4 are, we would like to have CXL HDM addresses. We will assign them CXL HDM addresses in the HDM decoder. And therefore, what ends up happening is while those two namespaces may have two sets of addresses, it only will respond to the CXL addresses. So over on the left, there's no memory backing that bar space. So it's effectively a hole in the memory map for the bar. So as I've mentioned, this is only an example. If your particular device does not want namespace ID 3 or 4 to be accessible with bar, if CXL is not available, then you would not request that as part of your request for bar space at the beginning of boot. All right, so to kind of summarize a lot of that information and then cover some new concepts, I've captured some notes here on this slide. So the work that is for defining this host addressable subsystem local memory is being done in NVMe TP4184. It is in architecture definition phase. We are progressing, but we would certainly welcome your input if you've got some suggestions on how you'd like to see it operate. Because it is still in architecture definition, there could be some minor changes based upon how it all plays out at the very end. So the SLM memory is accessible by the host and the device. That is true today with the commands, and obviously we're adding the ability to address that memory with the host address, and so it would be true still even with an address assigned by the host. So obviously the SLM can be addressed with a host physical address. Once we add this capability to any particular namespace, we can use PCIe bar or CXL, as I mentioned. The SLM memory itself can be read or written with SLM commands, host load store commands, or cxl.mem commands. And again, you may not be able to use all of those at the same time, depending on which of the three modes you select for any particular namespace. So the SLM memory that has a host address can have have a virtual mapping for host applications so that the host does not have to switch contexts for SLM memory access. If you're using the SLM with computational programs, The compute is still triggered in the same way with computational programs. Nothing changes in that respect. We're not doing anything to computational programs at all. The computational programs can utilize that host addressable SLM in the same way that it has been, it, but it just provides new mechanisms for the host and the device to be able to address that memory internally. We are enabling a peer-to-peer data movement based upon a host physical address, and we'll look at some examples of that coming up. And lastly, I just want to reiterate that the SLM is still accessible with the SLM command set memory read and memory write commands. So if you've got a device that you've already been working on and it has support for memory read and memory write, great. Those are still valid. Those are not going away. They're going to be valid for all of the different access types, no matter what. All right, well, let's take a look at some benefits. I tried to capture as many benefits that came to mind that I see for this capability. The first one is multiple access methods. We have the ability to now access that SLM memory in more than one way. We have the memory read and memory write commands, great, but now potentially we can just use load store and go write that memory directly, or use cxl.mem and write it directly or read it directly. And we'll look at some examples of this coming up. So load store access provides a low latency, fine granularity path to access the SLM. So this is really useful, especially if you have a small transfer. If we don't need to move a large amount of data with the DMA and we just need to write a few D words, using the load store is obviously going to be much more efficient than setting up a large DMA. So as I mentioned, we do want to support CXL. And so with that CXL support, we gain coherency with the SLM. The ability to read and write this SLM directly avoids copies and data movement. We can put the data right where we need it and then operate on it and then come back and read it. And we can bypass the host for any peer-to-peer type transactions. So obviously we've got two different methods. We've got the PCIe bar access and the CXL HDM access. So what's the difference between the two? Well, I think that the short summary of that is that the CXL allows coherency. We can have coherency with the host memory and the memory mapped IO space, whereas the PCIe bar access allows for load store access over PCIe architecture using uncached MMIO space. But we don't have the coherency that the same way that CXL provides. And so I think it really comes down to what do you need in your application? If you would like to be able to have coherent operations using CXL, then clearly that's the mode that you want to enable for that namespace. If you don't need that coherency, then maybe the bar access is sufficient for you. And of course, you can have multiple namespaces in your device, one with CXL and one with bar. It's entirely up to you. And then you can have the flexibility of both. All right, so to try to help understand this a little bit better, let's take a look at some use cases. So I actually have 4 use cases for us to look at today, and they all use a picture similar to the one over on the right-hand side of this slide. So let me walk through what this picture is showing us to level set so we can understand what's happening in all of the examples. So if we start at the top, we have our host, which has a couple of the subcomponents shown, the CPU cores, CPU cache, the host's memory, for example. In the middle, we have a fabric. This particular example uses CXL, so it shows CXL fabric. But again, if you don't need CXL, then you would probably just have a PCIe fabric. And then underneath that, we've got a computational storage drive. And you have all of the components shown internal to that computational storage drive. We have an NVM namespace. We have an SLM namespace. We've got compute namespace. What we're looking at over on the right-hand side of the computational storage drive is an expanded diagram of the SLM media. The intent here is to be able to more easily visualize what's happening to the media itself in the SLM namespace as we're moving data in and out. So as I mentioned, computational storage isn't the only time you can use host addressable SLM, but it is one case where there will definitely be more SLM available and would benefit from that host addressing. So it just makes for a great example. On the left side of the picture, we have our host coherent host physical address space. So this is just showing the address space of the host and the fact that we have carved out some CXL address space for our input data buffer for this particular example. And finally, underneath that address map is color-coded arrows. We have a solid green arrow representing CXL.mem traffic. We have a dashed brown arrow representing CXL.io or NVMe traffic. And then we have a solid blue arrow representing CSD local traffic, so something that's happening within the computational storage drive. All right, now taking a step back after having walked through that picture a little bit, we can start looking at this first use case. So what we have here is a data post-processing example before we write to storage. So in other words, we're going to move the data into the drive, we're going to perform some operation on that data, and then we're going to actually store it into the persistent media of the drive. So the value proposition of this use case is we're going to avoid copying data using DMA, and we'll take a look at how we avoid that copy, and take advantage of lower latency CXL-based direct load store access, which, like I mentioned, is especially beneficial if you have small input data. So our configuration for this example, we have our input data buffer is in the host addressable SLM that is configured for CXL. And we have an output data buffer that's just in traditional SLM. So it's command access only. All right, so looking at the actual steps, the numbers for the example correspond with numbers over on the picture. So in step one, we're going to write input the input data buffer using cxl.mem. And so we're using cxl.mem commands to put data into the input data buffer. When we're done with those writes, some or all of the data may still reside in the host cache on completion. No problem. We'll take a look at that in an upcoming step as to how we're going to handle that. So step two, the host issues an NVMe execute program command to the compute namespace. So the intent is that the compute namespace is going to read the data in the input data buffer, perform an operation on it or a manipulation, and then write it to the output data buffer, which is over in namespace 2. So in order for it to actually do that, of course, it needs to get all of the data into the input data buffer. Well, so because we are CXL aware in this example, the device is going to use a CXL back and validate snoop to keep the host cache coherent with the input data buffer. So essentially it's going to say you need to evict everything out of your cache so that it ends up over into namespace 1 in our input data buffer. And once it's in that input data buffer, now the compute operation can operate on the data in its entirety. So that happens. We do that that compute operation, and a completion is posted for that in step 4. Then the host issues an NVMe copy command to copy the data from the output data buffer to storage media. The data is copied to the storage media, which is in the NVM namespace, and then a completion is issued for that copy. And so we have fulfilled exactly what we had intended to do. We wrote the data to the input data buffer, performed a manipulation on it, and then ultimately wrote it out to the persistent media. And by writing to the input data buffer using cxl.mem, we obviously bypass the host. Instead of first having to write to host memory and then DMA from host memory to the device memory, we went directly to the host and stored it in the host, which of course saved a step. All right, so let's move on to use case number 2. So this is a similar use case, but it's going in the opposite direction. So we have a data pre-processing example before sending to the host. So in this case, we have our we have a similar value proposition. We're going to avoid copying data using DMA, and take advantage of CXL direct load store access for small input data. So our input data buffer is in traditional SLM in this case, so meaning we do not have host addressable for the input data buffer, and that's no problem. We don't need to for this example. The output data buffer is in host addressable SLM that is configured for CXL. So in this case, we're going the opposite direction. So the first thing we're going to do is issue an NVMe memory copy command to the SLM namespace, which is going to copy data from the NVM namespace into the SLM namespace and write it to the input data buffer. So that completes. And then at that point, the host will issue an NVMe execute program command to the compute namespace. Similar to example one, we're going to take our input data buffer, perform an operation on it. Maybe that's a decompression, maybe that's some other manipulation, and we're going to write it to the output data buffer. And so in this case, because we're using CXL again, we do have the ability to issue a back and validate snoop to make sure that there's that no data in the host cache that's about to be overwritten, so it can invalidate that those lines if necessary. So the compute namespace performs the operation of reading the input data buffer and writing to the output data buffer. And when that's finished, at that point, the application can come and read that data directly out of the device using cxl.mem at its convenience. It does not need to go, we do not need to DMA that data to host memory and then later read that memory into the host. It can just come and get it directly out of the device when it is ready. All right, use case 3. We have data post-processing with a standard SSD. So let's take a look at the picture, and what's changed here a little bit is instead of having a computational storage drive, we'd have a computational storage processor. So this is a device that's got all the compute capability, but it doesn't it isn't going to store any data. The storage is going to happen over in the standard SSD that's shown to the left of the computational storage processor. So we're going to put the data over in that traditional drive after we've performed an operation on it. So the value proposition here is that we're going to bypass the data movement through the host, and we're going to go off and perform a manipulation on the data and then write it to an adjacent drive or a peer drive that's connected on the same fabric. For this example, both the input data buffer and the output data buffer are in host addressable SLM that has been configured for CXL access. It could potentially have had the output data buffer in CMB, but that's that's a different example. So this example is both of them are in CXL addressable SLM. All right, so step one, the application is going to write to the input data buffer using cxl.mem. So this is identical to our use case one that we already looked at. We already know how to handle the situation where some of the data may still be in the host cache upon completion of those writes. We'll just use a back and validate snoop to make sure that that data gets flushed out to the SLM namespace. So we're going to issue an execute program command, very similar to example one. We're going to process the data in the input data buffer, write it to the output data buffer. All that is very similar to what we've already seen. Now, where it changes a little bit is in step 5, where the host is going to generate an IO write to the SSD NVM namespace. And it's going to configure that write with a data pointer pointing to our output data buffer in SLM, in the HDM. And it can do that because we have a host address to it. It's a valid system address. And we can say, here's the data as resides at this location. And the SSD is then going to use PCIe UIO for direct peer-to-peer access from that HDM space and write to the storage media. And at that point, it does become very similar to use case one, where we have now stored the data in our device. It just happens to be a peer device. All right, so use case 4 is another peer data processing example, and this is one that some companies are exploring. If we look at the picture, what we've got now is we've got a computational storage drive A and a computational storage drive B. And we've got some of our data in A, we've got some of our data in B. We need to get them all together into one location so that we can actually perform the computation. And this is interesting because frequently I hear people say, well, what if you don't have all the data? You've got, your data is sharded across a couple of different drives or multiple drives. How do you do compute operation on it? Well, this would be one way to do that, is we just get all the data moved over to one drive, and now we can go ahead and do the operation on it. And we're still offloading the host. The host isn't having to do that computation on the data. So for this use case, our value proposition is that we're going to bypass data movement through host memory. The configuration is that our data resides in a peer device. So in this example, it resides on drive B, and we need to get it from drive B's storage media into the input data buffer over on drive A. And so a way we're going to accomplish that is we're going to issue an NVMe read command to drive B, and we're going to set it up so that the destination is the input data buffer on drive A. And again, we can do that because it's a host address, and we can say write to this address on the read. So that data is going to be transferred peer-to-peer from drive B to drive A through the PCIe fabric. And when that read completes, then we can issue an execute program command and manipulate the data in the same way that we have already seen in example 1 and 3. Any number of operations this example could go any number of different directions. I have written the example so that we end up just doing the computation and then writing to the media on drive A. Obviously, we could make the data available to the host, whatever makes sense for the application. What's not shown in the steps is how to get the data from drive A into the input data buffer. We've seen that already in example 2 as well, where we can do a memory copy command to bring that data in. And so with all the data together now in one location, in one drive, we do that operation right into the output data buffer. And then, like I said, for this particular example, we're just using an NVMe copy command to copy that from the output data buffer to the storage media. All right, so to kind of summarize everything that I have shared, so we are enhancing NVMe technology to add host addressing to the SLM. The work is being done in TP4184. There will be 3 access methods. So we've got the command access only, which is what we have today. We have command access plus PCIe bar access. And then thirdly, we would have command access and CXL HDM access. And picking which method just depends on what capability you need in your device. Many benefits with this capability. We have load store access to NVMe SLM. We can potentially have coherency between the device, SLM, and the host. Obviously, it depends on if we pick CXL as our one of the access methods. We can take advantage of lower latency, especially for small transfers. So since the SLM is addressable with a host physical address, we don't have to copy data from host memory to SLM and vice versa, right? We can just come and read it or write it directly. And we've seen examples where we can bypass the host for peer-to-peer data movement. And of course, that certainly offloads the host. So I think looking ahead, that enhancing NVMe SLM to be host addressable is going to enable new use cases for computational storage. But not only computational storage, I think any application where you would like to have more memory and be able to address it inside the device. All right, so with that, I will pause for any questions.
Thanks, Jason. And for everybody on the line, please feel free to submit your questions via the chat feature, and we'll get to as many as we can today. The first question that we had is, why do we need host addressable SLM? Can't we simply use CMB?
So great question. So the answer is it depends on your application. If you're wanting to do some type of a computational storage application, CMB is not accessible by computational programs in NVMe. So Could we have enhanced CMB to enable computational programs to access it? We could have, but that only provided some of the capability we were seeking. And in particular, it would lack the ability to access the memory with CXL coherently. And so we really wanted to enable some additional capabilities than what CMB would provide.
Great. And then the next question is, why are there two potential host addressable methods for SLM? Isn't one sufficient?
So yes, it may be sufficient for your application, but it really depends on what your application is. So if you're wanting only the ability to address some memory down in there and you don't care about coherency, you don't care about accessing it with CXL, then sure, the PCIe bar access method would be more than sufficient. But as I mentioned in the previous question, some people are interested in being able to use CXL, and so suddenly it became clear that it would be best if we could provide flexibility, and through that flexibility, then an implementation or a user can choose which method makes the most sense for their application and what they're trying to accomplish.
Great. Well, if there are not any more questions, we can go ahead and close for today. So for everybody on the line, we will post these slides on the NVM Express website, and then a recording of this talk will be available on Bright Talk and the NVM Express YouTube channel. Thank you all so much for joining.